In mathematics, proof is often described as the soul of the discipline. However, translating that soul into a classroom setting presents a unique set of pedagogical challenges that researchers have struggled to standardize. General educational research frequently examines the relationship between teachers and students as a set of social or psychological dynamics that exist independently of the specific subject being taught. To see if that subject-neutral approach holds up in mathematics, a 2024 systematic review by Gabriel Styliades and his colleagues analyzed 103 high-level research papers published between 2018 and 2022. By categorizing these papers, the review identifies where the field is concentrating its efforts and where it is beginning to establish new theoretical frameworks for the classroom. The researchers used Cohen's triadic conceptualization of instruction as their map. This framework isolates the three primary actors of the classroom: the student, the teacher, and the mathematical content. The edges of the triangle represent two-way interactions, like student content or teacher content, while the center represents a holistic system where all three elements interact at once. Each of the 103 papers was assigned a position on this triad based on its primary research focus. This spatial mapping allows us to see the topography of current research and identify which areas of the didactical relationship are receiving the most attention. Looking at areas of the triangle not involving mathematical content, the student, teacher, and student-teacher edge. Out of 103 papers, only 4 focused on the student, 0 on the teacher, and 1 on their relationship without focusing on math. This near-total absence suggests that in this field, proof is more than just a context for a study. It is the core of the didactical process. These results indicate that for mathematics education researchers, the pedagogical dynamics of proof are inseparable from the mathematical content itself. The highest density of research occurs on the student content edge, where 49 papers are located. 44 are building ground, refining existing theories, while only 5 are breaking ground, introducing new ideas. Much of this work focuses on how students use generic examples and counterexamples when they attempt to form conjectures. Another significant theme involves how students comprehend indirect proofs, particularly the intuitive hurdles they face when working with proof by contradiction. This edge represents the most established area of the field, dedicated to clarifying and iterating on our understanding of how individual students process mathematical claims. On the teacher content edge, we find 13 papers. These studies examine how educators interact with proof through their own content knowledge and their decisions during task design. One finding in this area shows that teachers often perceive conjecturing and proving as two separate activities with different goals, rather than parts of a single mathematical process. This research suggests that teacher perspectives can influence whether students have opportunities to engage in unified mathematical practice. In the triad center sits the student-teacher content zone, studying all 3 instruction elements simultaneously. Despite having fewer papers than the student content edge, it boasts a higher ratio of breaking ground contributions, representing significant theoretical developments. These papers investigate the complex dynamics of classroom argumentation, established proof norms, and discursive habits of proving. Researchers here are developing frameworks for heuristic refutation, the process of revising a proof by identifying and addressing counterexamples. Others use cognitive frameworks to analyze the way a professor's feedback directly interacts with a student's written proof. This center zone represents a shift toward analyzing the classroom as a functional system, rather than a collection of isolated cognitive events. This diagram summarizes the findings. Bracketed numbers for breaking ground and building ground reveal where theoretical contributions concentrate. The pure content node holds 13 papers, 8 breaking ground. Combined with the center zone, data proves breakthroughs strongly correlate with keeping mathematical content at the forefront. The concentration of these breakthroughs suggests that expanding our understanding of math pedagogy requires a focus on the specific nature of the mathematics being taught. Between 2018 and 2022, research moved toward the holistic interactions of the student-teacher content center. For instructors and curriculum developers, these trends suggest that improving proof instruction involves addressing the interaction between student cognition, teacher guidance, and the content itself. By mapping these relationships, we can see that the most significant developments in teaching the soul of mathematics come from embracing the full complexity of the didactical triad.